Our final installment of the cubic workout, we're going to reach that goal. So we're getting to the finish line here, and your heart's pumping and your muscles are aching at this point. So what do we have up to this point? We now know everything we need to know about that middle column in our scaffold. Namely, we know how to find the value not only of any fully symmetric polynomial, but also of any partially symmetric polynomial in the roots of our cubic equation. And by partially symmetric, I mean symmetric with respect to the cyclic group Z mod 3 action. So everything in the middle here depends on the fully symmetric polynomials S1, S2, and S3, but it also is going to depend on an additional Z mod 3 symmetric polynomial, like P or Q or delta, right? But we know the values of all those things now. So any Z mod 3 symmetric polynomial, we can find its value. So our last step now is to go one more step over to the right, find the values of x, y, and z. We're going to do that by building up a 3x3 linear system of equations for x, y, and z. And we would like for that linear system of equations to have right-hand sides, let's say, which are numbers that we can compute by translating them into our middle column. And it's again that Reynolds averaging process that's going to get us from something which doesn't have any symmetry at all over here, and we're going to build into something which does have the Z mod 3 symmetry, and hence we can compute its value. And we're going to do so in a very delicate fashion, because what we're interested in ultimately is that we be able to go from this middle column to the column on the right by doing nothing more than taking a simple cube root. If we can do that, then we're golden. But as you'll see, it's going to require a very delicate process by which we look for a polynomial over here in the right-hand column whose Reynolds average is equal to its own cube. If that's true, then because its cube lives in the middle, we can find its value, and the cube root of that value will give me a linear polynomial over here on the right that becomes part of my 3x3 system. Once I have enough of those linear equations, I can solve the 3x3 system, and we are done. So let's reach that finish line. So now, ultimately what we need to do is take the last step to go to the right-hand column and find the values of x, y, and z themselves. So what we're going to do is we're going to hope to build up a system of linear equations in x, y, and z, because solving a linear system of equations never requires taking any new square roots, cube roots, or whatever. If we can build a 3x3 linear system, then we can find the values of x, y, and z. So what this is going to require us to do is come up with some polynomials that are in the right-hand column, which are linear in x, y, and z, so we can make a linear system. But we also want, just like when we were going from the left column to the middle column, we want to find polynomials that are proportional to their Z mod 3 relatives. In other words, when I apply a cyclic permutation, what I get is a scalar multiple of the original polynomial. And again, because of the group considerations, that proportionality constant has to satisfy k to the third power is equal to 1. In other words, we want to make it so that the action of Z mod 3 is exactly the same as the action of multiplying by a number which also has order 3 in the complex numbers. And there are three such so-called third roots of unity. We can think of them as being points on the complex plane. So it's almost like we're back to our table now, except that our table is really a complex plane. And to solve the equation k to the third minus 1 equals 0, all we really need to do is factor. And if you remember your difference of cubes factoring, it factors into k minus 1 times k squared plus k plus 1. And this gives us one solution, which is a real number, k equals 1. So that's going to be the plate that's sitting right here on the table, on the complex plane. And the other solution is going to come from solving the quadratic, k squared plus k plus 1 equals 0. And to solve that quadratic, I'm just going to activate the quadratic formula, which is going to tell me that k is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. And then all I have to do is reduce b squared minus 4ac into its numerical value, negative 3. And now I have found the other two solutions, which are not real numbers, they're complex numbers. Negative 1 plus radical minus 3 over 2. And on the other hand, negative 1 minus radical negative 3 over 2. And so there are my three solutions to k to the third power equals 1. And each one of these different values for k is going to become the constant of proportionality for another polynomial which is proportional to itself when we apply the action of Z mod 3 to its variables. So that's the plan here. And each one of these different values for k is going to give me a different polynomial invariant and therefore a different linear equation to solve in my 3x3 system. And so here we go, starting in the column on the left here. Let's start with the easy example. That is the proportionality constant k equals 1, the real third root of unity. So what am I looking for? I'm looking for a polynomial f1 which is linear, so it's going to have to be some linear combination of x, y, and z, but I also want to make it so that when I permute x, y, and z in a circle, when I do either the forward or the backward cyclic permutation, that the result is equal to 1 times that very same polynomial. The easiest way to do that is just to give my original polynomial the same coefficient everywhere. Let's just give it 1s, just for the sake of simplicity. So that now, if I trade x for y for z, z for x, if I apply that permutation, then again, all that's going to do is this. But because all of our coefficients were the same in the beginning, all those coefficients are still the same here, and then likewise here. Now I'll take those 3 polynomials along the orbit of z mod 3, and I'm going to multiply them together to find their Reynolds average, which is then going to be z mod 3 symmetric. Of course, that's not that interesting because our original polynomial already was z mod 3 symmetric. So in this example, it's kind of silly. But when I take that Reynolds average, what I find is that my proportionality constants multiply together and they disappear. 1 times 1 times 1. So what we find out is that f1 to the third is z mod 3 symmetric. And because it's z mod 3 symmetric, I can find its value. And that value is going to, in principle, depend on the elementary symmetrics, S1, S2, S3, and it's also going to depend on, something that's in that middle column, maybe P. But some combination of those is going to let me find the value of f1 to the third power, and then all I have to do is take a cube root to find the value of f1 itself. So that's our workflow here, is that when we make this Reynolds average, we land in the middle column, and we can find the values in the middle column just using the symmetrics and something like P. Then taking the cube root gives me the value of something in the right-hand column. Well, the process gets more interesting when we go to the other cube roots of unity. Let's suppose I want to find a polynomial which, when I trade places in my polynomial by sending x to y, y to z, z back to x, that what I get is equal to zeta, which is what we're going to call this primitive third root of unity in the second quadrant of the complex plane, times our original f2. So how am I going to do that? Well, here's an idea. Let's take our 3 coefficients x, y, and z, and let's make their coefficients exactly powers of zeta. This seems like a promising idea, because when I multiply powers of zeta by another zeta, all it's going to do is give me other powers of zeta, which are going to be no higher than 2, and so it's going to look like a carousel of my terms here. So if I multiply everything through by zeta, I'm going to get zeta here, I'm going to get zeta squared in the middle, and I'm going to get zeta to the third, which is equal to 1 here on the end. And sure enough, that's exactly the same thing as I would get by taking x, x and putting it where y was, y and putting it where z was, and z putting it where x was. Okay. So the action of x, y, z on this polynomial is exactly zeta times the original polynomial. Then if I do it one more time, multiply by zeta, multiply by zeta, multiply by zeta, again, the same thing happens down here. Okay. So each time the action of z mod 3 acts by scalar multiplication by the third root of unity. Then, computing the Reynolds average, I'm going to again find out that the Reynolds average of these 3 things, because each of the elements along the orbit is proportional to the original, my proportionality constants are going to multiply together and disappear, because zeta to the third power is equal to 1. And so f2 to the third power is going to be z mod 3 symmetric, because it is exactly the multiplicative Reynolds average of the original f2 that we started with. And again, that's going to allow me to find its value by finding the value of the cube using the elements in the middle column that we know, and then taking the cube root of that. And finally, for zeta squared, the only thing that changes is we're going to trade places with zeta and zeta squared. So really I've got zeta squared y, zeta to the fourth z. Zeta to the fourth is the same thing as zeta itself, so we could just write it this way. And sure enough, when I spin the carousel on this one, we're going to end up multiplying by zeta squared to get zeta squared here, zeta here, and then 1 here on the end. Multiply by zeta squared again to get zeta there, 1 here, and zeta squared there. And then when I compute the Reynolds average again, I'm going to have all of my constants of proportionality disappearing because I get zeta to the sixth, which is the square of zeta cubed, which is 1. And so f3 to the third power is also z mod 3 symmetric. So I can determine its value and then take the cube root to get the value of f3. And that's our way home here. We're going to have a linear system, and by solving that linear system, we're going to determine x, y, and z. And we will be happy campers. So now to finish the job, all we have to do is find out what are the right-hand sides of these linear equations by finding those values in the middle. So what that's going to look like is we need to take f2 cubed and f3 cubed. f1, by the way, we get away with not doing a whole lot of work on because f1 is fully symmetric. We're not going to have to work very hard to find its value. But f2 cubed and f3 cubed we do have to do some work on because we have to know how they relate to s1, s2, s3, which are fully symmetric, and p, which is partially symmetric in the middle. Okay. We can find out expressions for them in terms of s1, s2, s3, and p, and then simplify those expressions with the values that we know from our coefficients. And we find out that f2 cubed is actually negative 27 times zeta. f3 cubed is negative 27 times zeta squared. That takes a little bit of simplification, but again, Mathematica is very well suited to doing this. So that f2 is the cube root of f2 cubed, and f3 is the cube root of f3 cubed, and each one is respectively negative 3 times zeta to the 1/3 and negative 3 times zeta to the 2/3. So here we've found the values of these polynomials in the right-hand column, these polynomials that are not symmetric, by symmetrizing them and then finding their value as symmetric polynomials. And just to reinforce how this part of the process was done, Mathematica can be used to reduce a polynomial even if it's not fully symmetric. Again, it can tell us how it reduces into a symmetric piece and a remainder. So if I take x plus zeta y plus zeta squared z in Mathematica, and then I take that quantity and I raise it to the third power, which again, that's what we get when we take its Reynolds average because of the delicate way that we set up f2 in the first place. And then I want to know how that reduces into a combination of x's, y's, z's, and the symmetric polynomials. And so we get this rather nasty looking expression. But what you'll notice hiding inside of this expression yet again is that polynomial xy squared plus x squared z plus yz squared. That's p. So that explains the appearance of this p term in our final reduction. We can do the same thing for f3 cubed in a completely analogous fashion. So where are we at this point? We have three linear equations in the unknowns x, y, and z. The first of these was just x plus y plus z. This was the choice of the cube root of unity equal to 1. And because that is exactly an elementary symmetric polynomial, its value is equal to the value that Vietta's theorem gives it from the coefficients of t cubed minus t plus 1. That's the t squared coefficient, really minus t squared coefficient. And so that 0 is coming exactly from this 0 hiding right there. Okay. So that gives me the right-hand side of my first equation. The right-hand sides of the second equation were far more interesting, but again, the way we got those is by taking the Reynolds average of each one of these polynomials, which is going to be z mod 3 symmetric, and noting that because of the way we put these together, their Reynolds average is exactly equal to their own cube. And because that was the case, we could find the value of their cube because it was symmetric, and then take its cube root. That gave us the right-hand sides. So we have a 3x3 system of linear equations to solve that will tell us the roots of our polynomial once and for all. So all we have to do is do that. So I've turned it into a matrix equation down here at the lower right-hand corner of the screen. And now you can convince yourself that this is indeed a non-singular linear system. So it has a solution, and that solution is unique. So let's just go about finding that solution. So what I'll do is I'll just find an inverse for that 3x3 matrix. Again, I used Mathematica to do this part just because I was feeling particularly lazy. And then after all is settled, all the dust settles here, we find out that x, y, and z have the forms that you can see on the screen right here. And again, don't forget in this whole process, what is zeta? Zeta is -1 plus the square root of -3 all over 2. So that what you see in these examples is that what we're really doing for instance, in x, is that we're taking the cube root of minus zeta, so maybe I'll have 1 minus the square root of minus 3 over 2, and then I'm subtracting the cube root of that same thing squared. So negative 1 plus radical 3 over 2 squared. So this shows you how x, the first of our roots, is built out of a process of taking square roots and then cube roots. I have to take the square root of negative 3 at some point to give me that third root of unity, and then after I've done some of that, I have to take cube roots ultimately to build up my x. And in a completely similar fashion, we can build up the formulas for y and z to show us how x, y, and z are all built out of simple radicals taken of integers, which is fantastic. That was the point of this entire exercise. But in case you're itching to see something a little bit more concrete, I'm going to break my promise about approximation and look a little bit more closely at these roots. So remembering that zeta squared is the same thing as the conjugate of zeta, because zeta is a third root of unity here, this x is really the sum of the cube root of zeta with its own conjugate, and when you add a complex number to its own conjugate, you get twice its real part. And the real part of zeta to the 1/3, because zeta is a third root of unity, its cube root is a 9th root of unity, and its real part will be the cosine of 2 pi over 9. So x is negative 2 times the cosine of 2 pi over 9. That's one of the roots of our polynomial. Now, it doesn't look an awful lot like a polynomial root because it looks like trigonometry, but the shocking thing is that this really is an algebraic number. It really can be computed just by simple radicals, as we showed a moment ago. That's kind of special somehow, because not only can we use a triple angle formula for trigonometry to show that we can reduce cosine of 2 pi over 9 to something as simple as cosine of 2 pi over 3, which is rationally related to square root of 3, but also, geometrically, cosine of 2 pi over 9 is actually a constructible algebraic number because we can get to it via trisection of an angle. And trisection is a process that we can do with a compass and a straight edge. So our first root of this polynomial is actually negative 2 cosine of 2 pi over 9, which numerically is about negative 1.5. So if we take a moment and we get the graph of our function back into the picture here, we'll notice that, sure enough, that root, negative 1.5, is the one that we're seeing right there on the left. So there's x. Then the rest of the roots we can get just by simplifying out what we have. So we can rewrite y in terms of zeta and x, and then since we know what x is, we can get a number for that. So y actually, in this case, is our furthest to the right root, and finally z, after we simplify it out, gives us the root that's closer to the origin. So there are all three roots of this 3x3 system, and even though we had to approximate them at the very end, notice that each of x, y, and z, because of the way they're built out of zeta, which is built out of a square root of negative 3, and then the cube roots of such, shows us that x, y, and z really are algebraic numbers when it comes down to it. So this is the last slide I want us to take a look at one last time, because this shows us the full picture of what we just did. That in the left-hand column over here, we have a bunch of polynomials that are completely symmetric with respect to any permutation of x, y, and z. And because of that and Vietta's theorem, we can therefore, for any polynomial, determine the values of these symmetric polynomials, and that those values are all rational numbers. And that's always the case for any polynomial. Then all it took for us to go from this column to this column was to be able to take a square root. And once we were able to take that square root, now we can determine the value of any polynomial that's here in the middle, which is partially symmetric. Symmetric with respect to a cyclic action, but not with respect to the entire action of z mod 3. In our particular example, it turned out that because this delta here was a perfect square in the left-hand column, our discriminant in the middle column ends up also being a rational number, which is mega special. This definitely does not always happen, but these are all rational, again, because this was a perfect square. That's actually a theorem you can take to the bank, that whenever the square of the discriminant, which is always a fully symmetric polynomial, but when that takes on a perfect square value, then when we take its square root, we're not going to get anything new in the middle column, and the Galois group of our polynomial is going to be z mod 3. Again, I'm being a little intentionally vague about what a Galois group is here because I don't want to get into that part of the discussion, but this is how it connects with the day-to-day business of solving one of these polynomial equations. And then once we got into the middle column, we could get into the column on the right ultimately just by taking a cube root. But in order to make that work, we needed to find some polynomials over here on the right, which had that special property that their Reynolds average, their multiplicative Reynolds average under Z mod 3, was just a power of themselves. And using the cube root of unity, zeta, is how we built those up. And then we got a 3x3 system of equations, and solving that 3x3 system of equations will give us what we want. So that was the overall arc of this. But to finish up, let me ask this. What would happen if we chose a different polynomial in the very, very beginning? If instead of t cubed minus 3t minus 1, we were looking at something else? What would change on this slide? And the answer is not a whole heck of a lot. If I choose a different polynomial to start with, then I'm going to get different values here for the elementary symmetric polynomials, because these come directly from the coefficients of your polynomial, which means that the value of this squared discriminant is going to change. And if that value changes, then it changes the value of this delta here, which is going to change p and q. And because delta and p have changed now, that will also imply that the values of anything over here are going to change. So everything highlighted in red here is likely to change. Oh, and of course the solutions are going to change in general. What doesn't change is all the rest of the machinery that surrounds this. Right? That what we have here is a sort of a full and complete machine for finding the solution of any cubic equation through a process of first finding the values of fully symmetric polynomials like the square of the discriminant. I can find this value from the coefficients in Vieta's theorem, and then take the square root to find the value of delta. Then delta can tell me p. And then we saw how p combined with S1, S2, and S3, the elementary symmetric polynomials, can tell me the value of anything I need to know over here on the right, but not before I take its Reynolds average. And if I take its Reynolds average in such a way that I end up with a power of my original, then going from the middle column to the right column requires nothing more than a cube root. So the machinery is the same. And that's why we spent most of our time talking not about our specific polynomial, but about all of the symmetric polynomial machinery that surrounds it. So if I want to use a different polynomial, I'm going to start with different numbers right here in my Vieta's theorem box. But after that, everything else about the process is the same. And to me, that's the really fascinating part of this whole thing. There's a reason that I call this seminar talk a cubic workout, because like a good workout, it gets your heart going, it gets your blood pumping, it gets you thinking. And like any good workout, there's a purpose to it. I mean, the reason that you work out is to get stronger. And I believe by the end of this whole process of discovering how all this works, I think I've gotten stronger in my understanding of what Galois theory is and how it actually does help you to solve equations. So remember what the purpose was behind this. We showed how the group theory connections in Galois theory actually expose to us exactly what's going on when we're building up a formula, like a cubic formula, to solve a cubic equation. So what was really fascinating for me was just how much machinery goes into this process, and just how much the particular way that I put this all together, hinges on this process of taking a Reynolds average, taking everybody, rotating them around the table, averaging all their scores, and then suddenly we have something which didn't depend on which scorecard we looked at. That Reynolds average was used a whole number of different times throughout this process, and yet I feel like Reynolds averaging is not really talked about as much as it deserves to be. That because it's so flexible and because it can always give you a polynomial invariant for any finite group, is just bake your own polynomial invariant. It's incredibly useful in Galois theory, and I don't feel like it gets used enough. But it really did make our process here go round. And at the end of the day, what we got was, on that last slide, we really got a picture of an entire piece of machinery that all we have to do is, at the bottom left-hand corner, give it those coefficients. And as soon as I give it those coefficients, Vieta's theorem and the symmetric polynomial theorem tell us the value of any symmetric polynomial we want, and then those values can be used with a square root to determine the values of any Z mod 3 symmetric polynomial in the middle, and then those values with a cube root can be used to find the value of any polynomial at all over on the right-hand column, and in particular x, y, and z themselves. So I hope you found some of this interesting. It's a very long seminar talk, but feel free to send me any comments, any questions, anything I screwed up, because I'm sure I screwed up a bunch of stuff. Even if you're a professional algebraist and you want to write me and say, this stuff is obvious, I've known this stuff for a million years, please do that also. But for me, this was a great exercise in just really being as concrete as possible in what Galois theory is, how Galois theory works, and how we use a solvable group like S3 to get at the solutions of a polynomial equation like our cubic. I hope you enjoyed. I'll see you around the block.